terminated some resistive load such that the TDR plot is given by figure 2.60, determine the location and the value of the load.
I've got a, they want the value and the location of load?
Yes, sir.
All right. Let's see. Let's see. And so the plot I have to look at is 2.1.
2.60.
All right. So I'm going to try to explain this. We don't know the length of the line. With me? Don't know it. But here's what we do know. We have a pulse diagram that looks like this. Starts at 0. This is going to be, I'm assuming this is at the load end. This is the voltage. Is that right? All right. It's the measurement of the voltage at the load. And at, is it 7 nanoseconds?
Yes.
7 nanoseconds, there's a discontinuity, something that goes down, changes state. Y'all follow me on this, class? So if you think about this rationally, we're assuming the switch it closed at t equals 0. If they don't do that, we can't make heads or tails of this. We have to know something about when the actual event occurred, the beginning. All right, so it's initiated t equals 0, and here's the voltage at the source end, and all of a sudden it changes state 7 nanoseconds. So now rationally you have to say to yourself, well, how far did this pulse go? When you throw the switch at t equals 0, this thing's moving down at the velocity c over 2, then it hits and it returns, right? So it went 2L, correct, class? It went twice the length because it had to go down, hit, and reflect. So now we know the total distance traveled was 2L, right? And we know it took 7 nanoseconds. So therefore, now we just use basic physics. Velocity times time is distance covered, right? This is the distance. Here we have the velocity is c over 2, 50% of the speed of light, times some td, and the actual time is 7 nanoseconds, correct, class? Y'all follow the way I'm doing this logic. So this is 7 nanoseconds. Therefore, we have c, and I'm going to do it this way, if you don't mind. I look at this, I'm just going to say this. I can see I've got a 2 here. I'm going to divide both sides by 2. And I'm going to get right to L. All right? So now this is C over 4. Y'all follow what I'm doing? Everybody? That means this should be equal to C, which is 3 times 10 to the 8th meters per second, times 7 times 10 to the minus 9th seconds over 4. So what is that? It's 21 over 4 times 10 to the minus 1. And what is that? 5 times 4 is 20. 5 points something?
0.5.
Pardon me? Say again? 5.1?
0.525 meters.
Oh, 525 meters. Is that the answer?
Yes.
All right, but that's the rationale for this. Just realize this. Whenever they're talking about these problems and they've got, it's time domain reflectometry. This is the way you do it in a wall. If you want to find the length of a cable through a wall, you got to go and take out, if it's in a matched load like it's coax line, just put a short there. So then, you go ahead and initiate a pulse, you're gonna do a data recording on this on like a standard network analyzer or anything like this, where you let the pulse go, it hits, reflects back, and you see the time delay. That time delay gives you all the information about the length of the line. As long as you can assume something about the velocity of the line. Either, for most coax cables, it's about the speed of light, just slightly less. This 50% stuff, 50%, I mean, there probably is something like that, but that's a dielectric constant that's pretty darn large. Now, this is a little beyond the scope of this chapter's lecture, but when we talk about the velocity, well, actually we did talk about this, but we did it in a way where we talked about velocity on the line, the transmission line was equal to phase velocity, 1 over the square root of LC. You remember that? That was phase velocity. However, because I gave you, if it's a TEM wave, that L and C multiplied together were really the mu in the media times the epsilon. Do you remember that at all? So therefore, this is really equal to 1 over the square root of mu in the dielectric, epsilon in the dielectric. Well, that's 1 over the square root of mu naught epsilon naught times the square root of mu relative epsilon relative. This would be in the dielectric of the transmission line, because that's where the wave is manifest. The voltage occurs between the outer shield and the inner core, and it's the wave that's propagating downward. Now, here's the truth. 1 over the square root of mu epsilon, of mu naught epsilon naught is what? It's velocity of light, it's C, correct class? That's the fundamental definition. I'm going to replace this by C, right? Now, mu relative is called the permeability. It's always 1 for non-magnetic materials. It can only change, and there's nothing magnetic about the dielectric insulators. Do you all follow me on that? So we'll make that 1. Now we have this, 1 over the square root of epsilon relative. Here's my point. C over the square root of epsilon relative is equal to the velocity, which is C over 2, right? That makes epsilon relative 4, doesn't it? That's a fairly large dielectric constant. 4 is a big one, and you get that with some silicon dioxides and things like this, but that's not common with most things that are insulators. Like when you look at that, the plasticky stuff, most of the stuff that are insulators don't have that high of a dielectric constant. So this is probably a fictitious problem. Okay. Other questions about the TD? Because these plots, I'm going to do at least one, but I prefer to come from the audience for a question. Anybody? There were several that I gave you. How many actually took a look and did them? And don't worry, I'm not going to chastise if you haven't. What I just need to know is who I'm talking to. All right, at least about 50% raise their hands. So, any questions about the problem? Any of them? You want to do one? Nothing jumps off the page at you. Want me to create one? All right, I want to do one because there's a couple things that people mess up on these problems all the time.
Dr. Budinski, how do you get the resistor value for that problem too?
They didn't ask for it, did they?
Yes, they did.
They do?
Uh-huh.
It's like the value of the load.
All right, and so they give you 50 ohms here, and did they give you the value of VS or not?
Yes. One drops it.
All right, so this is one, okay, we can get it fairly quick. And it goes to 0.4?
Yes.
All right. Now I want you to think about, let me do a bounce diagram over here and I can reference it, then we'll get this value. We can get this fairly straightforward from the reflection coefficient. Does it give you anything about RS? Good. That disqualifies any thoughts I had about using it, because there is a way to use it, but not with that bounce diagram. So this was 7 nanoseconds. Okay. So here's my version of a bounce diagram for this thing. This is L, this is 0. In this direction, it's time. And the bounce diagram looks like this. This, from here to here, would be just TD. That's the time it takes to get down the line one time. From here to here would be TD. this total time here for the thing, for the wave to go back, or to hit the actual load and return, would be 2 TD. Now, take a look at this. It starts at VS, right? We know that, correct, class? Keeps going down, then it hits here. Then it's coming back and it has a reflection coefficient at the load times VS, right? Comes back and hits here, correct, class? Now, here's the thing you gotta understand. He's given us VS, all right? He doesn't give us R, does he? He doesn't, so he's assuming that is not a factor. So what you have to do is this, you have to say that when this wave hits this point, the summation of VS plus this has to be equal to this. Y'all with me? That value. So here, if we're actually doing a timing diagram, let's do it this way. We start here, and we go down, and we see that at this point, the value of the voltage would be VS, it's everything above, so it's VS plus gamma L times VS. Y'all follow me? By the way, that is the transmission coefficient at that point, but I'll get to that in a second. So VS is 1, so I know 0.4 would be equal to VS times 1 plus the reflection coefficient at the load. I'm just saying this, and I know VS is 1, correct, class?
Yes.
From the diagram, so I just leave it as 1. And now I can see what? I've got 0.4 is equal to 1 plus the reflection coefficient at the load. Or if I take -1 to this side, I have -0.6 is equal to reflection coefficient at the load. Do y'all follow me? Y'all agree with this? All right, now what is the reflection coefficient at the load defined as? Well, it's equal to the load impedance. In this case, it's a strict resistance, so I just call it R load, right? Minus the characteristic impedance of the line, Z0, it's the impedance I came from, over R load plus Z0. Y'all agree with that? Now, Z0 is 50 ohms, correct? I'll do it, I could actually normalize, but I'll just do it, I'll brute force this thing. I'm gonna multiply both sides by RL plus Z0, and I have minus 0.6 times RL plus Z0 is equal to RL plus Z0. I know Z0. So now I take everything, all the knowns, I'm gonna take all the Z0 quantities over there. So I get Z0 here plus 0.6 Z0. I'm doing it this way for a good reason. Then I have RL on this side. I have minus 0.6 RL minus RL. Can I do this right?
Dr. Briggsky, I think it's a negative on that right side.
Yeah, it is, it is. You're absolutely right, and that makes sense. And so that would be minus, and that would be plus. My bad on that, thank you. You all agree with this, class? Yeah. Okay, so this is gonna be Z0 is 50, and what is that equal to? 12.5, is that the answer? Let me make just one comment to be clear about this. The real thing is knowing that gamma L is equal to RL minus Z0 over RL plus Z0, and that the reflected pulse when it comes back is added to VS to give us the 0.4. That's the only trick in the book for this problem. Who asked that question? You did? Y'all follow me? So it's good. It's really showcasing how to go and determine things from timing diagrams like this, TDR. I want to go through one of these. Yeah. Did you have a question? Okay. Anybody else got a question related to this material? Something? Yeah.
So that was for resistance load. In the book, he briefly mentions if you have a reactive load, it will
Yeah, I don't cover that here, and the thing about reactive loads, it's going to be a differential equation. And we could go into that if we have a little more time, but generally speaking, when you have an inductor and you strike it with an incoming wave, the impedance of an inductor looks infinite the instant the wave hits. All right, it's like an open circuit. As the wave continues its persistence there, it looks closer and closer to a short circuit. Now, that means the reflected pulse from an inductor that you would get would be like an open circuit in the beginning, very high, and it would die down exponentially. I'll tell you, I don't go into that, but almost any kind of TDR work that you're going to be dealing with, I can think of at least, are going to have just resistive loads on them. If they have anything that's a combination, it becomes a lot more complicated because most things aren't simple, just inductors or just capacitors. They're combinations, and then it gets to be a much more difficult problem. All right, so that's that problem, and I want to do one with the timing diagram. But I want to do timing diagram at the load and midpoint. So here's going to be my fictitious, or I'll make it, I'll give actual values. I'm going to take a source and make the source plus or minus 10 volts. Then I'm going to have a source resistance, RS, equal to 100 ohms. Here, I'm going to have a transmission line with Z0 equal to 50 ohms. Now I'm going to have a line here, and I'm going to have a load here to be 25. And I'll make the length of the line L equal to 1 millimeter. Okay. Now, I'll call this 0 and this L. So I want two values of voltage versus time. I want the voltage versus time at this point right here, plus to minus V here, call it the midpoint. And I want the voltage versus time at the load. Follow me? It's important to listen to the second, but for the one with the load, right? Okay. So the first thing you have to do is create a timing diagram. Everybody with me on this? When you're doing a timing diagram, probably the place to start is getting the voltage that develops right here, T equals 0. And I call that V prime. Now, how do we get V prime? Oh, I didn't put a switch in. That's my bad. T equals 0. To start it at a non-zero point is kind of stupid. I mean, it's just not wise to do that. You always, if you're an engineer, start things at 0. If you start them at negative time or positive time, you have to skew everything by that amount. Okay, so when you're doing this, what is first thing we want to know what V prime is? How do we get V prime? Anyone?
Division.
Yeah, we're going to use voltage division, and our load here will just be Z0, correct? So now we get V prime, and we say it's just 10 volts times 50 over 50 plus 100, or 150, right? So that's 1/3, or 0.334 1/3 volts. Or sorry, 3.33 volts. Y'all agree with this? 10 over 3 volts. That's the voltage that develops here and propagates. Now, we do the bounce diagram by just setting it up the normal way. On the top, you just put a line here. This is L, this is 0. Then here you're gonna take something and you're gonna have time, right? Or just T. And so the bounce diagram looks like this. Hits here, comes back, hits here, goes this way, hits here, and so forth and so on. Okay? Now we get the values that we need for the reflection coefficient, the reflection coefficient at the actual load is equal to what, guys? Well, it's going to be Z naught, right? Z load minus Z naught, correct? So it's going to be 25. It's always the impedance you're going into, which is the load impedance, minus Z naught, which is 50, over the two added together is 75. Now that's going to be 25 minus 50 is minus 25, over 75 is minus 1/3. Do y'all agree with that? So this is minus 1/3. Then we have to get the reflection coefficient here, and that's the reflection coefficient at the source. And the way you do this is, again, you use the Thevenin equivalent circuit of this thing, or you look for the Thevenin resistance. That means you short this voltage source out. Do y'all follow me? You just take this as your effective load resistor you're going into, because the pulse is reflecting this way. So it would be 100 minus 50, or 50 over the sum of the two, or over 150. So here we have 100 minus 50, or 50 over 150, or this is plus 1/3. Agreed? Now we just go down here for this timing diagram, and when I look here, this is my V prime, which is 3.33 volts. I'm going to leave it as just V prime for now. Coming back this way is going to be V prime times minus 1/3. Y'all agree with that? Everybody? And that's the thing reflecting this way, correct? Y'all with me on this, class? How many see this? I'm sure you do. Now I could put minus 1/3 times 3.333, which should be minus 1.111, but I'm not going to. It hits here. Now this wave hit here. Now I multiply this incoming wave by the reflection coefficient there, which is 1/3. So this wave coming back is going to be V prime times minus 1/3 times 1/3, or minus 1/9, right, times V prime. It hits here, and then the wave coming this way would be equal to minus V prime, and it would be minus, we get rid of the minus. It's V prime, and then it's minus 1/3 times minus 1/3, so I'm just going to take minus 1/3 squared times 1/3, and that wave's going this way. I'm running out of distance, but y'all follow what I'm doing? Now after that, you should do this, or that's why it's nice to have graph paper, that engineering paper. And we need this, the time right here, because we know every time the thing goes down, this is going to be TD as well here. And so this point would be 2 TD, this point would be 3 TD, and so forth. Now we're going to do this bounce, and we'll get the values. And I asked for the value right here, right? So I want you to watch this. Some of you probably haven't done this. You need to be clear about this. I'm going to want the value in the middle of the line between the upper and lower conductor. And the way I'm going to get it is just go to the middle of the line. If that's L, this would be L over 2. Take a straight edge and draw a line straight down the center. Now, once you do that, then we're just going to go over here. And if you have engineering paper, it is perfect for this. I don't see anybody with engineering paper, but maybe there is somebody with engineering paper. You got it? Okay. Anyway, with engineering paper, if you take a look at this, here I'm gonna put TD over 2, this would be TD, this would be 3/2 TD, and this would be 2 TD. The reason I'm doing 1/2 TD is because if I trace this line, I start right here, as I'm tracing down, nothing at all is on that until I hit this point. So this would be the voltage at the midpoint. It would be 0 until I hit here. You all agree with that? Now when I hit here, that's the voltage that was propagating, so it just becomes V prime. And I know that V prime here is actually 3.33 volts, correct class? It just stays at 3.33 for how long? Well, you keep going down here and you see the next time this ricocheting pulse hits is down here, which would be at TD over with 3/2 TD. Do you all agree with that? Can you all see this? All right. So then when it hits here, what happens? Well, now I have to add this -1/3 V prime onto that, which means it's actually going to be 2/3 V prime. Do you all agree? It's going to go down. So it's going to jump down here, and that would be 2/3 V prime. I'm going to just put the 2/3 here. And it's going to stay there for how long? Until I hit what? 5/2 TD, correct class? And then what's going to happen? Let's take a look. Comes down here, hits here, right? Now, the wave that it interacts with is this wave, right? Which is going to be -1/3 times 1/3 of -1/9 V prime, so it goes down again. Do you all see this? It's going to go down again. So now it's going to be 2/3 -1/9, so that's 4/9 -1/9 is 3/9, so it's 1/3. So this would be V prime right here over 3, and it's going to stay there. We could keep going on and on about this, but you all see how to get a bounce diagram for the voltage developing in the middle. It would be the same at any point. If it was going to be at only a quarter of the wave, or a quarter of the length down the line, then you would draw a line here, and you would do the same thing. Only now, the first change would occur at what? TD over 4, correct class? And then the next change would occur, now just follow me on this. Well, from here to here would be 2 TD, correct? But I have to subtract a quarter and a quarter, so it would be TD, right, times 3/2. Wouldn't it, class? Y'all follow me? It's basically going to be this point, which is, if you, actually, let's see. Yeah, it would be from here to here, the change would occur at 3/2 TD. And you can keep going on and on about that. You with me, everyone? Okay, so that's how you would go through here. I mean, we're dead center, the change occurs every TD, all right? And so forth. Now, I'm gonna do the bounce diagram for this guy below. This is the one people mess up, so I want you to hear me. And I'm gonna erase that. Because there's a common mistake here. This is going to be voltage at the load. Now, I bet you could figure it out, but just listen to me. It's going to go down, V prime's going down, it hits the load, right? But look, simultaneously when it hits the load, there's a reflected pulse that occurs instantly. That means you have to add the reflected and the incident pulse together there. Do y'all hear me on that? It means you have to add V prime plus the reflection coefficient or times V prime, or really the first voltage that occurs at TD right here is going to be, it's going to go up, and this one will be V prime plus the reflection coefficient at the load times V prime. Now for our case, since this is V prime and this is -1/3, it's going to be 2/3 V prime. And now I'm gonna make a comment that you're gonna hear over and over again in EMAG 1 and 2. If you have 1 plus the reflection coefficient at the load or source, that is called the transmission coefficient at the load, pow sub t. Because that's how much of the wave is actually transmitted to the load, the voltage. With me? Remember, as soon as this thing hits, instantly there's a reflected wave. So you have to add the reflected to the incident wave at that point. Y'all with me on that, class? That means that's going to be different. Now, how long is it going to stay at that value? And what would that be? 2/3 of 3.333 is 2.222, right? About. Correct, class, for this problem? So this is 2.222 volts. How long does it stay at that point? Well, the pulse took TD to go down here, another 2 TD, right? Then another one, so 2 more TDs, all right, delay times go down, we have to go through. So this is the point, next point it changes, right? And what do I have to add there? Well, think about it. I'm down here now, right? Do y'all follow me on this, guys? What do I have to add? I have to add this incoming wave, right? Plus this outgoing wave. Y'all with me? So the incoming wave is going to be V prime times minus 1/9. And I'll put it down. I'm just going to show you what I'm going to add on to this. This stays, this value stays, and I'm going to add on to that V prime over 9 with a minus sign. That's this wave. What about this one? This is minus 1/3 squared times 1/3. So that's what? 1/9 times 1/3 is going to be 1/27th, isn't it, class? But that's a positive, so I'm going to add that plus V prime over 27. And that's going to be a negative change, so it's going to come down a little, and it's going to stay there for another 2. Now, by this time, most of you see that every bounce reduces the amount of change. I mean, as time goes by, what your mind tells you, it's going to settle to a constant value on the line, and that's absolutely true. And this is the point I want to make next. When I take a look at this transmission line, as time goes to infinity, all these bounces just die out to nothing. And this transmission line looks like just 2 pieces of wire that are connected at a very short distance. And therefore, the voltage at the load is nothing more. The final voltage at the load, called V load final, will just be equal to voltage V source, and then you use voltage division, but Z0 has nothing to do with it. It's just RL over RL plus R source. Are you with me? So it looks like the transmission line isn't even there as T goes to infinity. All the voltage at the load is dictated by its value and the source resistance, and of course the 10 volts or the source current. Okay? Everybody see that? Keep that in mind. Because what you'll see some people do, let's see this thing growing, and you'll see the voltage going to infinity when they write computer programs, and somehow they misplace, they do something a little wrong. That would be an error, and that's a sure way I can take a look and see if they know what they're doing. I haven't done this. I don't usually do it in this class anymore, but I used to require it, and I think Whitmore still does this, but I'm not sure. He'll have you write a MATLAB code for this, and you'll print out the actual. When you see the voltage going to infinity, something's not quite right. Any other questions about this? Because this is really the thing I wanted to today I wanted to focus on that. Yeah?
So that's for like a step function where you have a positive value. If you're sending like a rectangular pulse.
If you had a pulse,
settle out to 0 because.
here's what you do. You make it the sum of 2 step functions. All right. What you do is take one. Basically, let me explain what he's talking about. It's a very good question. He's saying, what if this is not that? What if it's a pulse? What if this generator is a pulse generator? And what if the actual time domain signature of the source looks like this? If it goes to, say, V0, and then at some tau it goes back, or at some tau here it goes to 0. You with me? And you put that in. How do you do that? Well, it's simple. You say this thing right here, my Vs of t, it can be written as some V0 U of t. Y'all know what a U of t function is, right? U of t is just a step function. And then subtract from that V0 times U of t minus tau. Now that's the definition of a pulse with two U. Y'all know what U of t functions are?
Yeah.
How many do? I'm looking to make sure I get 100% back there. Of course. You can see the person on the phone back there. We'll discount that. But anyway, most people know what U of t functions are. So then the logical question is, well, what do you do with this? Guess what? You take the same exact waveform, or the bounce diagram for this, only now you put a negative sign in front of it, and then you time delay it by tau. Now if you want to, we can do that one, but it really isn't a stretch. It's just basically taking this waveform, and then you're going to get the bounce diagram, like the one we had up there, and you're going to subtract from it the bounce diagram, same exact bounce diagram, only now you just multiply it by a negative sign and shift it a little. Or just add them together, I'm sorry. Multiply by a negative sign, add them together. If you want, we can do it. I don't usually ask that because it's fairly obvious if you think about it. Really, you're only looking for the bounce diagram for the U of t, and then the duration. I'll tell you the trick about these. If I had this bounce, suppose they gave me this, I would do the same exact bounce diagram I did for this one. I'm just going to draw something up. I don't remember what it looked like. Suppose we do it midway. It was something like this, and then it went down, something like this, all right? Here's what I do. I get the bounce diagram for V0 U of t that I put up there, and now I know the duration is tau, correct? So right there, it goes to 0. You with me on this? Now that's after it hit. I mean, that's after the first part of the wave. Where's the next time there's a change? Here, right? And if you remember, this one's a little less. So then it would be this. Well, actually the change occurred right there. You're going to go ahead and have this, but now the duration here would just be tau. This duration would be tau. So every time there's a change that occurs, you let that change persist for the length tau, because it exterminates itself after tau, right? And that's the way you do those. They're not very hard. Y'all follow me? What's going on there? I can do one, but it's not that big of a deal. They don't usually ask that on a quiz. Just be aware of that if you're trying to do that. Okay. Other questions? That's a good question. I mean, we can make these as complicated as we want. We could literally get an infinite series of pulses coming in and ask for the net bounce diagram. And we could do it, but it doesn't have much meaning in the real world. My next topic is going to be chapter 3. We're going to be talking about electromagnetic fields that are caused by static charges, just electric charges. Now, most of you have had, all of you supposedly had physics, right? One thing physics does is really focus on the fundamentals that define whatever physical system is out there. And electrostatics, by the way, all physical laws are based on measurements. Everything. They derive things mathematically that come from measured data. So when we talk about electrostatics, the first thing we say, if we have a charge Q, call it Q1, and we have a charge Q2, and they are a distance r apart, as such, then if we wanted the force on Q2, are measured laws. We would go ahead and take the first charge value, multiply it by the second charge, and charges can be positive or negative, remember that. Then you would divide this by 4 pi epsilon naught, and we divide that by the magnitude of r squared. So it's inversely proportional to the distance between the two centers. By the way, and 1 over r squared dependence is the same thing we see for the gravitational force of attraction between planets. Same law, 1 over r squared, different constant in front. Now, the one thing about a force is that's the magnitude when it has direction. All right, so we need a unit vector, AR, that starts in the direction, basically its origin is Q1 and it lands on Q2 in terms of the direction it's pointing. It's pointing in that way, away from Q1 towards Q2. This is AR. So how do you get a unit vector is the next logical question. The real way is this, you first need a vector. So what we're going to do is talk about vectors now for a second, R. I'm going to say my vector R, and I'm labeling it this way. It has to have a beginning, has to have an end. I'm going to say its origin is Q1, it lands on Q2. So my direction is that for R. With me, everyone? Now, how do I get R? Technically, if we're in Cartesian coordinates, what you do is you take the coordinates of the point you land on. We're going to start with the x coordinate, call it x2. Subtract from it the coordinates you started with, x1. That's the AX direction. And likewise, you would say plus y2 minus y1, AY, plus, and this would be z2 minus z1, AZ. And here, I'm saying that this point is at x1, y1, z1, and this point is at x2, y2, z2. You all with me on that? How many remember vectors? This is, I'm not trying to talk down to you. I know, I think I had this in 8th grade, 7th grade, something like that. Just want to make sure that we're all on the same page here. Because vectors can be talked about a couple different ways. And they have different meanings depending on the actual classes you're in. Vectors mean completely different things in computer science. So, this is a vector, magnitude and direction related to a measurement system. When I take a look at the magnitude of that vector, it's equal to just the square root of the sum of the squares of these terms. x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. That's the magnitude. And we take a look at a unit vector, AR. That's simply R vector divided by R magnitude. Now, most of you know that, but that's how you get a unit vector. It's always something that has a magnitude of 1, and in terms of its total length is always 1, and it points in a unique direction that defines something related to the problem. So this would be AR. Are you with me? Now, I want to show you something that's done a lot of times. Instead of writing it like this, there's a couple of things that happen. We talk about physical laws. We can say that FQ2, force on Q2, always proportional to Q1 and Q2. By the way, Q1 and Q2 would have the units of coulombs. I didn't say that, but units of coulombs. And then, instead of divided by 4 pi epsilon naught, we can multiply by a constant K. And here, let me go ahead. Epsilon naught is really 1 over, the way he does it in his book is 1 over, I think, 36 pi times 10 to the minus 9th. Really, epsilon naught is about 8.854 times 10 to the minus 12 farads per meter. There's a reason he does it like that. Now, if that's epsilon naught and the units would be farads per meter, if I look at 1 over 4 pi epsilon naught and say it's equal to this constant K I'm going to show you there, well, that's 1 over 4 pi divided by 36 pi times 10 to the minus 9th. Y'all see that? This would be what K is? What do you notice that is? Well, the pi's cancel. I have 4 over 36 or 1 over 9 times 10 to the minus 9. Or this is 9 times 10 to the 9th. That's what you may have seen in physics. A constant K used at that. So that's this value of K, you can have it. And then what they do is this. Instead of putting AR by itself, they replace it with R prime and magnitude of R. Now you see, this really should be magnitude of R squared. When I replace AR with R vector over R prime, that becomes cubed. And what we get is R vector over R magnitude cubed. Y'all follow me? This is another way of writing the force equation. Either one are correct. This just puts the entirety of the unit vector right in there. You don't have to calculate it separately. How many remember seeing it? Kind of, sort of. Electromagnetics, really, electrostatics and physics used to be a very big deal. They'd have you measure pit ball separation and try to figure out the charge on each, if you remember that. If you haven't done it, it's okay, but they'd have all sorts of little laboratories you could do with electrostatic repulsion and attraction. And so this is another way to do it. Now, that's what the force is from a single charge. I'm gonna run out of time if I get too far ahead of myself, but I wanna say this. If we wanted the electric field at this point, the electric field at this point where this charge is has nothing to do with the actual value of the charge here, just the value of the charge creating it, all right? So the electric field at that point, usually what they do is say, well, we'll divide the force by the charge at that point to get the electric field, and that's correct. So if I wanted the electric field at this point 2, electric field at point 2, technically I would take the force right there at Q2 and divide it by the magnitude of Q2. This is the electric field. And let me say one other thing about this. I didn't do this because I guess I'm too casual. The units of force are newtons, right? They're not pounds, they're newtons. What is it, 4 points something, 4.5 or something like that, newtons is, I don't care. That's in newtons. Remember, we use the MKS system. That means we use kilograms, not pounds. For force, I guess it was slugs in the English system. We don't use the English system of units. And epsilon is farads per meter, or epsilon naught. So when we look at the electric field, the units are volts per meter. And the electric field would just be Q1 over 4 pi epsilon naught magnitude of R squared, AR. I can write it this way, it's the same thing. And that would be the electric field. The units of the electric field that we use are volts per meter. We're not going to use any kind of CGS units or other units. I know in physics, a lot of times they like to use the English system. We use MKS engineers, and the reason is that everything seamlessly transfers. You don't have to do a whole bunch of unit conversions. If you're dealing with electric power, if you're dealing with heat and all that stuff, BTUs are fine in the English system. But if you want to deal with all these things, like heat is in joules, it's in it. Anyway, that's it. We'll pick it up from there. I only had 5 minutes to give you a dabble of this stuff, but you've had this, right? I'll give you some reading, some problems. We'll talk about the force, and then we'll get on with this. And for the quiz on Friday, it will be on the bounce diagram. Amazing. Who would have thought that? I'll still get an email. What's the quiz going to be on? Get on this final paper.